You can make a soap bubble by blowing air into a soap film. Since you are forcing air into the bubble by blowing with your mouth, clearly the pressure inside the bubble is larger than the pressure outside the bubble. Yet the bubble remains in equilibrium. In other words, the bubble does not continue to grow, or collapse on itself. Hence there has to exist another force that is countering the pressure force due to the higher pressure inside the bubble. This force is called surface tension. In this section we will learn how surface tension works, and some important applications of this force. A liquid molecule that is within the bulk of a liquid experiences equal attractive forces by other molecules from every direction. Molecules that are at the surface of the liquid, on the other hand, experience an unequal pull from molecules that are in the bulk of the liquid. This is due to the fact that the gas and vapor molecules above the liquid exert a much smaller pull on these surface molecules, as compared to the pull of the molecules from the bulk of the liquid. The unequal force pulling the surface molecules causes the liquid molecules in the surface layer to be more closely packed than the liquid molecules within the bulk of the liquid. The net effect, which is referred to as surface tension, is that the surface layer of the liquid tends to behave like a membrane that is under tension. The surface tension effect causes the surface of the liquid to act similar to a membrane that is under tension. In a way, the surface of the liquid behaves like the surface of a trampoline. When the surface of the trampoline is flat, it generates no vertical force. Since the tension force is directed in a parallel direction with respect to the surface. Yet the surface of the trampoline can support a weight that acts vertically against the surface. This is due to the fact that when a weight is placed on the surface of a trampoline, like the block shown here, the surface deforms by curving downwards. The curvature of the trampoline's surface causes the tension force to have a vertical component that acts to support the weight of the block. The tension in the trampoline's surface also increases due to the deformation of the surface. But the trampoline can still support the weight of the block, as long as the maximum tension that would rip the fabric of the trampoline is not exceeded. In a similar fashion to the way the surface of a trampoline can support a weight, the surface tension force can support a small weight that is placed on the surface of a liquid, as the surface locally curves under that weight. Some insects use this property to literally walk on water, like the shown water strider. Notice how the water surface is curved under the legs of the water strider. This allows surface tension to produce a net upwards force that supports the weight of the insect. Mosquitoes use the surface tension force also to walk on water after they hatch. The surface tension force can support objects that have small weights but that are much denser than water, like a coin or a paper clip, if they are carefully placed on the surface of the water. These objects, if placed within the bulk of the liquid, would immediately start to sink, due to their high density. It helps if the surface of the object is coated with oils so that it repels the water molecules. A very light and flexible thread loop is suspended within a wire ring. The wire ring is then dipped in a soap solution, causing a soap film to form within the wire ring. Being surrounded by the soap film from every direction, the net force on the thread loop is equal to 0. Hence the thread loop floats freely within the soap film. The soap film that is within the thread loop is then carefully punctured. Finally, we observe that the surface tension force from the remaining part of the soap film pulls the thread loop to form a circular shape. In this section we will talk about how to measure surface tension, using a simple experiment with a thin circular wire. Then we will make some observations about what affects surface tension, talk about the units and value of tension force, and work through an example. Then we will discuss force on a soap bubble, the force on a droplet or bubble, and then finally we will work through another example. The force due to surface tension can be measured using a simple apparatus, like the one shown here. That consists of a thin circular metal wire that is connected to an accurate vertical balance. The wire is dipped into a liquid such as water. Then the force that is measured by the balance is observed as the wire is pulled out of the water. We will make a plot of the force divided by the weight of the wire versus the depth to which the wire is submerged. The weight of the wire is equal to the density of the wire times the gravitational acceleration times the volume of the wire. When the wire is fully submerged within the water, the forces acting on the wire are gravity and buoyancy. The force measured by the vertical scale is equal to the weight of the wire minus the buoyancy force that is exerted by the water. Substituting ρ wire GV for W and ρ water GV for the buoyancy force, we get that the force is equal to ρ wire GV minus ρ water GV. Assuming that the density of water is equal to half the wire density, then we get that the force is equal to ρ wire GV minus 1/2 ρ wire GV, which is just 1/2 ρ wire GV. But notice that this is equal to 1/2 of W. In other words, the force measured by the scale, divided by the weight of the wire, is equal to 0.5. Assuming that the height of the wire within the water is equal to 0 at the surface, the scale gives this reading of 0.5 for any wire height below 0. When the wire is at the surface of the water, a peak force is observed. In this case, the force that is measured by the balance is equal to the addition of the weight of the wire and the surface tension force of the water that is acting on the wire. We assume in this case that the observed surface tension force is equal to 0.1 times the weight of the wire. Hence, the force is equal to W plus 0.1 W, or 1.1 W. Hence, the force measured by the scale, divided by the weight of the wire, is observed to be equal to 1.1. Finally, when the wire is pulled clear of the water, the force that is measured by the balance is exactly equal to the weight of the wire. In other words, the force measured by the scale, divided by the weight of the wire, is equal to 1. Let's review. We've observed that for this particular wire and liquid, the ratio of the force that is measured by the balance to the weight of the wire, when the wire is submerged, is equal to 0.5. And the force ratio when the wire is at the surface is 1.1. And the force ratio when the wire is above the surface is 1. Press the play button to replay the movie. Then when you wish to continue with the lecture, please press the play button at the top. Now that we know conceptually what will happen when a thin wire is pulled out of water, let's try to evaluate the value of the surface tension force based on some observations from this experiment. First, we note that if the wire length is doubled, by doubling its radius, the surface tension force is also doubled. This implies that the surface tension force varies directly with the length of the wire. Our second observation is that if the thickness of the thin wire is doubled, the surface tension force does not change in any appreciable way. This implies that the wire thickness has no effect on the surface tension force. Finally, we observe that if the circular wire is replaced with a plate that has the same radius, the surface tension force is reduced to half its value. This means that the surface tension force on a wire, divided by the surface tension force on a plate of the same radius, is equal to 2. This implies that the surface tension force acts on the periphery of objects that are in contact with water. The peripheral length of the plate is equal to 2 pi times the radius of the plate. The peripheral length of the wire is twice the peripheral length of the plate. Due to the fact that the wire has both an external and an internal peripheral length that is in contact with the water's surface, as the wire is being pulled out. The value of the surface tension force can be obtained based on the aforementioned observations. The surface tension force varies directly with the length of the object's periphery that is in contact with the water. Hence the surface tension force is equal to a surface tension coefficient, which is denoted by the Greek symbol gamma, times the length of the object's periphery, or L. In the case of the wire, the length of the internal and external peripheries of a wire of negligible thickness is equal to 2 times the circumference of the wire. Thus the surface tension force that acts on a circular wire as it is being pulled out of a liquid is equal to 4 times the surface tension coefficient, gamma, times pi, times the radius of the wire. The surface tension coefficient has units of newtons per meter, or dynes per centimeter. The conversion factor between the two units is given as 1 Newton per meter is equal to 1000 dynes per centimeter. In other words, 1 millinewton per meter is equal to 1 dyne per centimeter. The shown table gives the surface tension coefficients of several common liquids, when they are in contact with air at room temperature, or 20 degrees Celsius. The surface tension is given in millinewtons per meter. Note that the surface tension of water is 72.8 millinewtons per meter. We will use this information in the following example.